Right. Okay. Right. So the last time we look at how the nearest neighbor classifiers work, let me briefly discuss the main points that we have discussed. The first of all, compared to decision tree algorithms that we have seen earlier, there was no learning phase. And simply learning here, what it means, it simply store the instance themselves. That's why we call it instance-based algorithm. And the storing data or training data as a model we call rote learning. So how similar uh, the instances are what is used in nearest neighbor. For example, when you want to make some prediction, that is the place where the learning happens in nearest neighbor, where it calculates the distance from the starting point or the guess point to all the other instances, which we call the similarity. So usually if you have numerical data, then obviously you will use what we call the Euclidean distance or geometrical distance to make the calculation. So therefore, this is normally known as lazy learning algorithm compared to decision trees, which is known as eager learning, because the learning is delayed until you will get a test instance. So there are two methods mainly we can discuss: simple nearest neighbor, one nearest neighbor we call, or just we say nearest neighbor, or we use k nearest neighbor. So here k is a parameter, which means the number of nearest neighbors you want to make the decision. Right, now having said that, the mainly we need to discuss how to calculate the distances. If you have a one numeric attribute, simply you can take the difference. But of course, if you have several numeric attributes, usually we prefer to use Euclidean distance, which we call the Euclidean distance. But what if you have a categorical data? Categorical data means, for example, outlook, we have sunny, overcast, rainy, and so on. If you have a nominal attribute like that, how do you calculate the distance? So then usually what you look at the values. If the values are the same, we say the distance is 0. If values are different, we say the distance is 1. The next question is whether all the attributes equally important, because you treat them equally important, and then assume that you have some attributes are more important than the other, then we need to use weighting. So that's how the usually we work with the nearest neighbor algorithm. Right, now if you look at the distances functions, usually we can commonly use Euclidean distance. You get the difference of each attribute value, square them, and you find the sum for each attribute, and then you get the square root. This is square root, sum of square roots of the distances. But then again, there's another metric is quite popular. We call city block or Manhattan. We just look at the differences. But then again, you can generalize this distance function. So when you generalize, we can say mean Minkowski distance, which you guess the differences multiplied or up to the p, the power of p, and then you get the 1 over p to get the Minkowski distance. So which means if you put p is 1, it will provide you the Manhattan distance. If you provide 2, it will lead to Euclidean distance. Right. So let's look at some example. So in this particular example, let's say you have 4 points. Now the idea is, now in this particular case, actually I'm going to discuss you how you may calculate the distances among the instances. But at the same time, when you're given a test instance, same technique could be used to predict the label. So let's assume that you have a data set, and then let me put up the labels. So for example, we can say that, okay, these are positive values. Let me say we'll put green. Okay, let's assume that these are positive values. So we will have points like this. So then let's say we have negative values, right? So it's like this. So what do you think if there's a point come here? Let me say I have put, okay, brown color, and I'll put a cross here. What do you think? Yes. What is the output of the nearest neighbor algorithm? Right. So in this part, I will actually going to talk about how to calculate the distances. So let's focus on the Manhattan distance, where we get the absolute values. So you first calculate the difference between the x1 and x2. So this is x1 and x2. So for example, x1 here, we know it's 1 and x2 is 3. So you get the difference. So if you take the distance L1, right, between x1 and x2, you get the absolute values and then you sum them. So the absolute value is 1 minus 3, that is 2, plus then 2 minus 5, 2 minus 5, right? So what happens here, we will get 2 plus 3, that is 5. And then that's how we calculate the Manhattan distance between L1 and L2. Okay, now can you give me the answer for x1 to x3? Right, so you can see here when you calculate the Manhattan distance between x1 and x3, we get the absolute value x1 minus 2 absolute value plus 2 minus 0. So this is 1 plus 2, you will get 3. So the correct answers given by Rishant, Tini, and Prasad. Thanks. So let's repeat the same for Euclidean then. So the difference between the Euclidean is simply we will use, right? Obviously, we are using L2, let's say x1 and x2. So the calculation now you get the difference and square them, and then you have to get the square root of this. So therefore, when we take x1 and x2, we talk about the Euclidean distance dl2 between x1 and x2. So between x and x2, what we need to do is 1 minus 3. We have to square them, plus then 2 minus 5. We have 2 minus 5. You have to square them. And then you get the square root. So obviously this is 2, that is 4. Plus this is 3, that is 9. That is square root of 13, right? So square root of 13, which means if you get the square root of 13, you will get 3.6. So when you get 3.6, so I can say the distance here using Euclidean, this will become 3.6. Okay, can you tell me the Euclidean distance between x1 and x3 then? So if you calculate correctly, and then you should get these answers, so which will give you the distance among these data points. So whenever you have a new data point, and then you want to predict, you have to perform the same. You will see that, okay, which point is close to the new test point. But remember, this is for the simple nearest neighbor, which means you get only the nearest instance. If you set k to 3, then you have to look for the 3 nearest instances, and then based on the majority vote, you have to make the decision. Right. But then there are a few things you have to note, especially the nearest neighbor will get the differences and then square them. This might be problematic if you're using different scales. So therefore, if your attributes are measured with different scales, you better normalize them. So when you normalize, what it means, you can actually do two ways. Simply, you can subtract minimum and get the distance between the max value and the mean value, and then you will get the normalized attribute value. Or you can use average and standard deviations. Again, similar to that, you can actually normalize. So always remember, if you apply nearest neighbor algorithm, you better normalize your attributes. The next one, if you have nominal attributes, either you have 0 and 1. So it won't create that problem, because it almost the same. But if you have missing values, then you have to use some policy how you treat them. So assuming that it's important for you to use missing values, then you can think that they are maximally distinct, right? Given the normalized attributes. Right. Having said that, if you finalize what we need to discuss under this, so most of the time you will notice that nearest neighbor algorithm will provide you accurate estimate. But on the other hand, they are slow, and then especially when you have a very big data set. So therefore, sometimes people used to use tree structures to minimize this. Same way, if you look at the attributes, we assume that all attributes are equally important. But in real practical problems, attributes may have different importance. So then you should apply some weights. Then if you have noisy attributes, then of course, you can actually consider the parameter k. Now here the k means how many instances we are going to consider. For example, if you say k is equal to 3, that means you select the 3 nearest instances, and then based on that, you are going to make the decision. But problem is, it's very difficult, right? Come up with the accurate result. Right. Okay. So with that said, let me show you how we will perform nearest neighbor implementation. Right. To do that, I will come out from this, and then I will start wake up. So I told you, like, we need to use Explorer usually. So we can click on Explorer. And within this, usually we start with the pre-process tab. We can open a file. That part also we did early. So you can select particular installation. So in our case, we have installed our programs under program files. And I have two various versions of Wake-up. And you can go down to the data folder just to see like what data is there. So now you can look at what information you have. The simple ones we discussed last time is weather dataset. So the first one is weather nominal, which is we have a categorical data. If you want to see what is inside, you can click on edit button, which will give you the information about the data. And you can see we have 4 attributes and they are nominal. There's another version which we call weather numeric, which when you open up, you will notice that there are numeric datasets as well. Outlook is nominal, temperature is numeric, humidity numeric, and then wind is nominal. So this one we have when we can say it's mixed data. Similar to that, if you take, for example, breast cancer, and then if you go to edit, you can see again it's a mixed data set. We have nominal data. Mostly we have nominal data, although we have some numbers there. Again, if you look at contact lenses, we have again nominal data sets are there. Then diabetes. And if you say edit, you can notice that it's almost numeric, right? So which is very good, especially for nearest neighbor kind of algorithms, because naturally you have numerical data. So let's try to classify them. Of course, you can use other algorithms as well. For example, decision trees, for example. You can go to tree structures and you can choose C4.5, which is implemented as J48. And then you can build the tree. And then you can visualize it if you want. So for example, in this particular case, you will get outcome like this, right? Tree structure. And then you can actually also look at the accuracy values, which I will discuss later on. Currently, if you carefully look at the accuracies for the decision tree, we'll get about 73.82. So now let's try with some lazy learning algorithms. You have to go under the lazy, and then IB1 means nearest neighbor, IBK is K nearest neighbor. So I'm going to first select IB1 first. Let me say start, right? And then there's no outcome because there's no training, but testing is used. So in this particular case, we'll get about 70%, which uses the Euclidean distance. So that distance you can actually look at from here. And then if you want to change the K, then you can actually look at what you need. Let's say I'm going to select K to 3, so I can change 1 to 3 here. And then you can also select other information. Right here, we just say 3. So therefore, we are going to find out 3 nearest neighbor accuracy. So when I click select, So you can get 72.65, right? So let me change again. Let's say KNN is, we'll set to 5. Okay, let me run. We'll get about 73.17, right? So let me change again. Let's say KNN to 7. Of course, we get much better accuracy. So therefore, you can notice that the change of K we will see that when you increase, you will get increased accuracy. At some point, it might start to decrease. But therefore, it's very important that you test the best K value for nearest neighbor algorithm. Right. So the question I actually asked you to do is perform nearest neighbor algorithm accuracy for the K value for 9. The right now I changed the number of neighbors to use as a 9. And when you rerun, you can see the accuracy is a little bit low compared to the previous one. So according to what we have tested so far, then the K7 is the best according to my experiments. Okay, so with that said, let's move to the next part. Right. The next part, we are going to look at another machine learning algorithm where we use statistical modeling. So if you look at in general what these models are, this is mainly opposite of 1R. I hope you remember in 1R, we consider only one attribute at a time. And instead of that, here we can consider all the attributes. But there are two assumptions. Usually, the first one is they are equally important, and then they are independent to each other. We here means that statistically independent, right? Right. So now let's see, although we made all these assumptions, in real practical scenario, these assumptions are not valid most of the cases. But in practical applications, we have noticed, or you might notice that it's always true, or you get better accuracy compared to other algorithms, right? Therefore, these algorithms work well in practice. Right. So as we have discussed in the previous section, this works very fine, even though there are some issue of independent assumption. The idea here is this, the probability estimate, there might be any changes, but as far as you get the maximum probability assigned to the correct place or the class, you are safe, right? But on the other hand, remember, if you have too many, then that also be problem, right? So that is what we will see with the naive Bayes. So the model for the naive Bayes is simple probability table, something like this. This table, in this table, we will notice that for each attribute, we have count number of times the particular attribute value appears. For example, if you take Outlook as sunny, so there are 5 instances out of 5, 2 the outcome of 2 instances are classified as yes and 3 as no. Overcast, all the instances are classified as yes and 0 as no. Rainy, we have 3 and 2, right? Okay, so now we calculate the probability values. So given that we have 9 positive instances, we divide each value by 9 to get the probability value. Similar to this one, we also divide by 5 to get the probability value. That is how we calculate the probability values. Now I have a small question for you. Given the count for the temperature, hot we have 2, mild we have 4, cool we have 3 and 1. Can you tell me for hot, what is the probability being the class is yes? What is the probability for class being no? So ideally what I expect you from you is what is the value given this hot? Yes. What are the probability values being classified as yes and being classified as no? Yes, as Prasad says, this is the positive. We have 9 instances. Out of 9, there are 2 instances under hot. The no, we have total count is 5. So the probability is 2 divided by 5. And you can continue the same. Okay, good. Next one. Now use our data set to calculate the count for humidity, high and normal, and windy, false and true. Let's start with the humidity. So how do you do this? Simply, we have to first look at our data set. So I hope you remember our data set. We have discussed it earlier, where we have 14 instances, and this is we call weather data set. So in weather data set, we had, right? How many? 14. So I'm going to share with you the data set. I will put you in the chat. Our data set. So I hope everybody got the data set. Now, having got the data set, I want you to look at how many times for the humidity. 2 values, high and normal, and see how many times yes and no appear. So look at how many times, let's say, first look at high. We have no, humidity high, we have no, we have yes, we have yes. Again, no. Again, yes. How many times? We have 2, 2, 3, 3. So you have 3 and 3. 3 yes, 3 no, right? Look at normal. If you look at normal, again, yes, no. 2 yes and 1 no. 3 yes, 4 yes, 5 yes, 6 yes. Right. So now that we have seen this, let's look at the probability values knowing your class value. So that's what we are going to look at here, right? So given this, if you apply this one, see whether you can understand, right, the probability values. So you can notice that we have 3 and 4, and this is 6 and 1. You divide by 9, these are the probabilities. Similar goes with windy. And then finally, for the class attribute play, here are the values. Now, given this table, the next one is, and this is the model, remember, in 9 base, this will be the model, right? This will be the model. So now let's look at how to calculate the probability values. Now, probability values are used when you get a new day. So here is a new day. We have to calculate values for yes and no, right? So you have to calculate the values for yes and no. So let's see. We will first call the likelihood values because that's what we will have. So we'll first of all, we call likelihood. Likelihood values. For yes value, here is how we are going to calculate. Now outlook is sunny. We have to get the value from our table. So look at the table. Again, I will give you the table for you. Otherwise, you might not understand the calculation. So you need to first get the probability values for the weather data set. Right. See whether I'm actually sharing the details in the chat. Right. Here are the probability values. Hope you got the probability values. Right. Now let's look at how we can do things. We have to first calculate the likelihood values for yes. Right, let's calculate the probability values for yes. So when outlook is sunny, right? What is the probability of being yes? Outlook is sunny. So you go to the table where outlook is sunny and calculate the probability. That is 2 out of 9, right? And you have to multiply this when you have temperature cool. Okay, what is the probability given class value yes for temperature cool? Yes. What is the probability when temperature is cool, given that the class label is yes? If you look at this with the temperature cool, right, is a 3 out of 9, right? So we will type 3 out of 9 multiplied by humidity high. Look at humidity high. Again, 3 out of 9 multiplied by last one. So that is wind is true. Look at the wind is true. Again 3 out of 9. And finally you multiply by the class being yes. The probability is 9 out of 40. So this is 9 out of 40, which is, if you calculate this, this becomes 0.0053. Okay, calculate same for no and tell me what is the likelihood value. So for no, outlook is sunny, right? You look at outlook is sunny. For class is no, 3 out of 5. Then look at temperature cool. So when temperature cool, 1 out of 5. Then look at humidity is high. When humidity is high, for no, 4 out of 5. Then wind is true. So wind is true for no class, 3 out of 5. Into finally the class no, that is 5 out of 14. And if you done the calculation, we'll get 0.0206. I think Rakshana's answer is correct. Now that we have got the likelihood values, remember what we need to do is naive Bayes is probabilistic one. We want to calculate probabilities. Now the problem with these likelihood values that we have calculated, they will not add up to 1. So therefore, we have to convert these values to probabilities by normalizing them. So what we could do is we can calculate the probability of being yes, right? We get the value 0.0053. We divide by the addition of both, which should normalize. So similar to that, no. Right? So now when you find the values, this should add up to 1. So what are the values? Can you do the calculation and let me know the values? So this one, if you solve correctly, you will get 0.205. And this is 0.795. And if you add this, will add up to 1. So the idea is, you can see the outcome of naive Bayes is, in this particular case, you will see, given a new day, the outcome is not yes or no. Actually, if you look for one answer, you have to say that you can't, the play should be no because you have a largest probability. But this is probabilistic classifier, which means you can say something like, okay, 79.5% time it's no, and 20% 5% time it's yes, or roughly you can say 80% of the time you can say no, and 20% of the time you can say yes, which is how we talk about the probabilities. So I hope you got an understanding about how the naive-based classifier works and also the model that we create. So when we say a model, it's simply some probability values. Right. Okay. I think we got the understood how this works. So the idea that we calculate the probability values, and then given a new date, we calculate first the likelihood values, and then we'll convert into probabilities. So this idea comes from the what we call the Bayes rule. That means given a evidence E, we have to find the probability of event H. We will write like this. So with the independence assumptions, so we can actually have given event, we can calculate each of these evidences, and then you divide by PE. So here we can talk about prior probabilities and then posterior probabilities. So in our case, when we talk about the evidences, E will be the instance and hypothesis will be our class value. So therefore, we can convert given evidence to calculate the probability for the hypothesis. We can calculate, since they are independent each other, we can use the naive assumption, and then given each class, we can calculate for each evidence. So let me explain this with example. So if you look at our weather data set with our previous one, now let's say we want to calculate the probability of being classified as yes given the evidence, that means our data point. What we need to do is we can break into find prior probabilities, which means like for a given the class value yes, becoming outlook is sunny probabilities, and this is what we have calculated. You multiply with given the class is yes when temperature is cool, given the class is yes humidity is high, given the class is yes wind is true, and then we multiply by probability of yes pay, and you divide by probability of the evidence E. So you can get this part exactly the same thing that we did earlier. Now, this is only for yes, and same thing can be done for probability of yes, no as well. And then when you normalize the same equation that we have used earlier, this probability for evidence will be cancelled out and you will get the outcome. Right. I hope now you got an understanding about the theoretical basis for this as well. Now, let's move on another example. Right. Predict the class value of this date. Right. Now we have discussed how we can find out when you're given a new instance. Right. So let's see whether you can calculate the class for the given date, Now there's a small issue here. What was the issue? So Prashantini, notice this, the overcast, if you look at the overcast, and if you look at the probability values that we have calculated, right? The outlook is overcast. And if you're trying to calculate for no, then there's a problem, right? The probability is 0. So what happens if you multiply with 0? Everything becomes 0. So that is a problem. So this problem is known as zero frequency problem, right? So if you look at some particular class values, the attribute value doesn't occur If it doesn't occur, then that will create a problem. Then probability values will be 0. Right? So then this is when we calculate the probability 0, irrespective of other values, then everything will become 0. So how do you handle this? There are many ways that you can handle. So the remedy is you can add 1 to count for every attribute value combination. So if this problem arises, right? So you can add 1 for every attribute value. If you ask me why this is working, this is called Laplace estimator. Why this is working? The reason is, right, the probabilities will never be 0. That is first one. The second one is, although you don't get the correct answer, but it will assign the highest probabilities for the correct class. Remember the idea that we have discussed. Therefore, you will get the correct answer. So what you need to remember from this point is, sometimes when we calculate the attribute values, this might happen. Okay, now try with what we have discussed. So given this one, we want to calculate the outlook overcast, temperature cold, humidity high, and the wind is cool. So how do you calculate? So now we have to look at the probability values that we have calculated, right? For example, outlook is overcast. So 5 divided by 12 and 1 divided by 8, right? Temperature is cool, 4 divided by 12, 2 divided by 8. Humidity is high, 4 divided by 11, and 5 divided by 7. Wind is true, 4 divided by 11, then 4 divided by 7. Finally, 10 divided by 16, 6 divided by 16. Yes, what is the value we are getting? So what we could do is, we can say 4 years. We can say 5 divided by 12 into 4 divided by 12 into 4 divided by 11 into 4 divided by 11 into 10 divided by 16. Yes, what is the answer when you do this? Is it 0.0115? So for no, 1 divided by 8, 2 divided by 8, 5 divided by 7, 4 divided by 7, 6 divided by 16. So is it 0.00478? Can you check? Okay. So when you normalize, what is the value you are getting? Yes. So probability of B yes equals 0.0115 divided by 0.0115 plus 0.00478. No, 478. So roughly this would be something like 0.7064. And ideally you will get 0.2936. Yes. So given this one, we can say 70% of the time you can say yes. About 30% of the time you can say no. Right. So I hope you are clear about what we did. The problem that we encounter is what will happen when you have a zero frequency problem. The idea that we have discussed is we add 1 to each and every value, which we call Laplace estimator. Actually, you can add any value, not necessarily this, right? So that can be decided. Okay, so what about the missing values? If you have missing values, right, remember, in training time, when you calculate the attributes, you don't include the frequency count. Classification, when you want to find out, you don't use that. For example, if you don't know outlook is missing, then you don't use outlook for the calculations. That's all what we do for missing values. Right. So for example, here you can notice that we only consider the temperature, cool, humidity high, and windy true, and we'll calculate the probability values. Next one, what if you have numerical data, right? So there's another numerical data set which you can actually use. I'm not going to talk about the calculation, but briefly talk about how we can implement those. So for the numerical attributes, we have to assume some probability distributions. So we can assume either the numerical attributes are normally or Gaussian distribution. So then to calculate the probabilities, we have to use probability density functions. So assuming that you have mean mu and standard deviation sigma, the density function we can define as 1 over square root of 2 pi sigma e to the power minus x minus mu square divided by 2 sigma square. So given numerical data set, what you need to do simply, you calculate the mean and variances, and then you apply this application. For example, let's say we want to know probability value. Given the class is yes and temperature value 66. So you have been given the value. So you apply to the equation, right? And then you can find the value for this. And this could be applied in the calculation. Similar to this, given humidity is 90, you can calculate the same. So once you know this, given these values, you simply use those values for the calculating the first the likelihood, then normalize to get the probability values, right? Again, similar to what we discussed early, if you have missing values, you can actually ignore them. Okay, to summarize what we discussed, naive Bayes compared to 1R, we are going to consider all the attributes. And I told you that attributes are independent, and then which is not correct in most of the cases, but we get the correct accuracies, right? But then you can have adding too many redundant attributes will have a problem, right? Okay, so those are the things that I would like to discuss for today. So let me show you now in Veka, how do you use this? For example, if you go to the same data set, and simply what you need to do is you select naive Bayes classifier. So naive Bayes classifiers are under the base. So I will select naive Bayes, and you can see that you can actually change values here. I'm not going to change anything here right now. I'm going to use a default value. And then when I say start, right, you will get, for example, the probability values like what we did earlier. And then it will give us the accuracy. So for example, we can go and open up the weather nominal database data set that we have discussed. So use, let's say, the naive Bayes, and let me say start. You can see how it was calculated. Remember, notice that it's already add one. We have already done this part. We have seen this earlier. These are the what we call the how we call the probability values, right? So we have done the calculation by hand. So I hope now you are very clear about how you may actually find or use naive Bayes classifier. With that said, I will conclude my session for today. So in the next week, we can talk about more on clustering algorithms and association learning. And then once I finish this with Weka, then I will start implementation in Python as well. Any questions, please? Okay, if you have no questions, then we'll stop for today. Thank you, everyone.